I would like to welcome you all for yet another IRENA seminar. Let me introduce myself. My name is Manti Saxena. I'm part of the IRENA online seminar organizing committee for this year, and I will be the host for today's seminar. I'm currently working as a postdoc at Ohio University. So let me now welcome our today's speaker. She's Dr. Gwen Grinyer. Currently, as of 2017, she's working as an assistant professor at the Department of Physics, University of Regina in Canada. She did her PhD from University of Guelph in Canada. So between her PhD and the current position, she was working as a postdoc at NSCL, Michigan for 2 years. After that, Dr. Grinyer was a permanent research scientist with the CAA and worked at GANIL in France for about 7 years. So her research broadly focuses on studying properties of exotic nuclei located far off from stability. And today she will be sharing some of her exciting results from the experiments she has performed at TRIUMF and at GANIL. Just a quick note, before we jump into the presentation, I request everyone to keep themselves muted. If you have any questions during the presentations, please feel free to unmute yourself and ask the speaker directly, or you can type in the chat and I can read the questions at the end of the presentation, or you can yourself wait until the end of the presentation and ask in the Q&A session. So let me once more invite Dr. Grinyer to begin her presentation. So the floor is all yours whenever you're ready. Please go ahead.
Okay, thank you so much for the invitation to give the talk today. I'm going to talk specifically about, well, some of the research we do related to radioactive decays or radioactivities. And we're going to kind of go on a voyage from kind of near stable isotopes all the way out to the drip line. So the talk's going to cover some of the big questions we have in low energy nuclear physics. I'll start there, and then try to convince you that studying radioactivity is an extremely powerful tool to study the atomic nucleus. And as I said, we're going to move from stability, so sort of get reacquainted with nuclear beta decay, and then move all the way out to the drip line where we see some really interesting kinds of decays like delayed proton and even 2 proton radioactivity channels that open up. And I'm going to talk a bit about some of the projects we're working on to be able to detect these really interesting decay products, namely a new project we're building here in Regina and a time projection chamber that we built in France. So with that, I'd like to start here. This is kind of like the table of elements for a nuclear physicist, the chart of the nuclei. So we plot proton number on the y-axis, neutron number on the x-axis, and every little black square here is one of the stable isotopes. There's about 288 or so of these, but we know from experiments in the lab that we've been able to produce something like 3,000. These are radioactive or unstable isotopes. They decay back to the stable isotopes. But we predict in this sort of red cloud that there could be as many as 7,000 of these isotopes that exist. You also see on the plot these dashed lines. These correspond to the nuclear magic shell numbers that we know from stable isotopes. And you also see these little gray lines. These are the RP process, the rapid proton capture process that occurs in explosive nuclear astrophysics scenarios. And on the neutron-rich side, you have another process called the R process. And you see that that passes through a huge swath of these isotopes that we've basically have no access to. Okay, and why is it important to go out there? Well, in terms of the origin of the elements that we see all around us, we think that something like 50% of all of elements that are heavier than iron are produced by this R process. You see the process goes right through a huge number of nuclei that we don't have access to. And even theoretically, it's very difficult to predict their properties. And the plot here shows you the elemental abundances in black that are measured in the universe. And in red or in blue are sort of theoretical extrapolations, whereas if you take what you know from stable nuclei and extrapolate, you see you get these blue curves that don't represent at all what we observe. And so we think there's this weakening of structure that moves towards extremely exotic nuclei on the neutron-rich side. What we need, though, to actually calculate our process, these intricate rate calculations, are nuclear structure inputs, things like masses of the nuclei involved, their half-lives, and how they decay. These are essential properties that go into predicting these abundances. Experimentally, though, this is extremely challenging. It's very tough to get to these nuclei. Many of them are impossible to access in the lab and probably will remain impossible forever. Theoretically, though, our predictions have large uncertainties, so we have to really study whatever we can with this limited number of nuclei as we have available to us. In the picture on the right, this is, of course, an artist's rendition of a very famous event detected in LIGO of 2 neutron stars merging. And we think that this, our process, this pathway that goes through all these neutron-rich nuclei, that a neutron star merger could in principle be one of the locations in the universe where our process is actually taking place. So basically, 2 neutron stars are the fuel that's producing all these really radioactive, highly neutron-rich nuclei that are producing then the elements in the universe that we see all around us. In this plot too, if neutron stars are the fuel for the R process, they're actually a very interesting have a very interesting structure themselves. A neutron star is not just made of neutrons. In the outer core crust, where it's cooled off a little bit, we actually have extremely neutron-rich nuclei that can live out there in some sort of equilibrium between decaying out and neutron capturing. And so you can actually sustain extremely radioactive neutron-rich nuclei in the crust. This is just one example of an article from a couple of years ago where they measured the mass of this nucleus here, zinc 82, and you see in this plot, it's right at the boundary of experimentally where masses have been measured. Beyond that, though, there's many isotopes for which we know nothing about. So this is the predicted edge of where the isotopes are in this region. And what they determined was even from a single mass measurement of 1 nucleus, they found that this particular isotope was much less bound than expected. And that updated completely the structure of the neutron-rich isotopes out in the crust of a neutron star. Of course, most masses and decay modes have never been measured out here, but this is just one example where even a single measurement can actually be very worthwhile in telling us very important details about the structure of neutron stars and what's driving this R process. For a lot of other applications in not just nuclear astrophysics, but just in nuclear structure physics in general, we have found over many, many years that every time we kind of leave this stable region and move either to the neutron-rich side or the proton-rich side, a lot of really interesting new phenomena open up. So you can see, for example, in nuclear structure, there's shell evolution that takes place where those magic numbers that we're used to near stability just kind of break down or evolve. We see even on, for example, the proton-rich side, I'm going to talk about this later, even new types of radioactivity can form, like 2-proton radioactivity that was only discovered in this century. Some of the big questions that we're trying to address with this physics that we're doing are kind of shown here. The nature of physics beyond the electroweak scale. How does the structure of nuclei emerge from the nuclear forces? And how are the elements formed in the universe? So this is quoted from the Canadian Subatomic Long Range Plan. You can find it on this website here. But the questions are very similar as well to the US NSAC Long Range Plan as well. And of course, a big part of what I do is to try to perform experiments on these most exotic nuclei to help answer some of these fundamental questions. Okay, so I'm going to start with a kind of brief intro to nuclear beta decay, because I'm going to talk about it a lot in this talk. It's an extremely powerful technique to study nuclear structure in general. And you know there's 2 types. There's beta minus decay, which is basically a neutron in the parent nucleus decaying to a proton in the daughter nucleus, and you get out an electron and a neutrino. Beta plus is if you're on the proton-rich side, those excess protons can decay into neutrons, creating a positron and a neutrino. There's 3 kind of fundamental quantities that we have access to experimentally, and that is for the parent nucleus that decays down to the daughter. We can determine the half-life of that particular decay. We also can measure the energy, the change in energy between the 2 states. That's called the Q value. And if you have excited states in the daughter nucleus that you can populate, we can measure the branching ratios to those states, which are just the fraction of beta decays that populate each state. And for beta decay near stability, once you populate these states, they're excited, and then they can emit electromagnetic radiation in the form of gamma rays that then de-excite down to the daughter ground state. Okay, so there's some momentum conservation and selection rules in beta decay. The words that I'm going to use a lot are, for the case of L equals 0, which is an orbital angular momentum transfer, we call these allowed decays. And you can have higher order L transfer in nuclear beta decay that are called forbidden. We're going to focus on allowed today. And then depending on the spin coupling between the neutrino and the beta particle, if they're anti-aligned, they're S equals 0 total sum, and we call these Fermi decays. And if the spins are aligned, we call them gamma of Teller decays. Okay, so that's just the wording between allowed, forbidden, and Fermi and gamma of Teller transitions, but it's rooted in these kind of selection rules that we, so we're going to come back to that. When you go further from stability, what happens? Well, the Q value opens up considerably, and you have a much higher decay energy that is going to be emitted when that parent decays. But what's interesting about this is that now you've got access to a whole pile of states potentially up here, and you might think that they also would gamma decay, but in fact, what happens is they're actually above a separation threshold, where there's such a highly excited state that they are actually more likely to emit particles rather than an electromagnetic transition down to this daughter ground state. So you get a proton daughter, in this case on the proton-rich side, where your beta decay populates those excited states, but rather than gamma decay, they just emit particles. And we can measure these protons that come out. This is a process called beta delayed proton decay. So it's a beta delay because it has a long half-life. And then once you populate the state, which is proton unbound, it immediately emits a proton. And this is what we call beta P, but you can also have beta 2P, so a delayed 2 proton emission. And you can also open up other channels like 2 proton radioactivity, and all kinds of other stuff can happen when you're really far from stability. Experimentally, what we do, we can produce these parent nuclei at a rare isotope beam facility, and then we can let them decay, and we can measure the various particles, like beta particles that come out. We can measure the photons and the protons that come out, and we can deduce basically everything on this plot, where the levels are, what their energies are, what their branching ratios are. We can measure half-life, so we can basically reconstruct this whole level scheme here. The other thing on this plot that I just wanted to highlight, because I'm going to come back to it, I've highlighted a very important state here called the isobaric analog state, which is just a daughter state that has precisely the same quantum numbers as the parent state. And so from a wave function point of view, these two are identical states. The only difference between them is that a proton has been converted into a neutron configuration. But basically, these two are identical states, differing only in a Coulomb shift between them. And then the other important quantity here is this separation energy, which is the energy above which those states can emit protons down to the ground state. And this is basically just a mass difference between the proton daughter and the beta decay daughter. Okay, so you're all familiar with a nuclear half-life. So how long does it take for half of the nuclei you have to decay away? And I like to plot it or put it in this table in terms of the half-life for the various classifications that I mentioned, going from allowed, so L equals 0 transitions, whether they're of the gamma of Teller or Fermi type, and then up to very high L transitions up to the 4th forbidden. And you can clearly see just from the half-life that the higher L you have to overcome, the much, much longer it's going to take for that beta decay to occur. And I took these numbers from this summary here in this article. And these are just single examples to show you what they are. But if you sum up all the different types, there's actually 64% of all beta decays that we know about are allowed transitions. About 33% of all of them are first forbidden, and then all the rest are just very tiny amounts So there's very few fourth forbidden decays known. And that's just because if a nucleus has another way to decay rather than a fourth forbidden transition, then it's going to go the faster route. And then so you won't see that anymore. But basically 2/3 of all nuclear beta decays are allowed. And what I'm going to focus on today is not just the half-life, because you can see there's a strong correlation between half-life and this sort of L value, but rather than half-life, we actually characterize nuclear beta decay not just by the half-life, but by something called the FT value, which is just the half-life multiplied by some other stuff. And the other stuff is the Q value that goes into this F parameter, and then we divide by the branching ratio to that state of interest. Okay, and then you can see from these FT values, which are proportional to half-life, then you can see from this correlation that the FT value tells you as well something very important about the L value of the transition itself. And the only reason we do this is because we can then define a transition-dependent FT value. And when you write it out, you can show that this quantity is related to some constants divided by some strength in the matrix element between the parent and the daughter states in the transition. So it's just a convenient way to write it. And then we call it the FT value. And that's kind of the parameter that we always talk about. I'm going to talk today about only a specific one, a specific FT value related to this very special case of 0+ to 0+ transitions. And these are allowed nuclear beta decays that are of the pure Fermi type. And you see they're pretty rare, only about 1% of all decays are like this. And we call these the super allowed transitions. And you'll see why in a second. The reason they're super allowed is because it turns out that this term on the right, which kind of looks complicated, hugely simplifies to a constant in the limit that, that these transitions are pure Fermi allowed, super allowed transitions between isobaric analog states. Okay, so if you want to make a simplification here, there's the numerator is a constant, and so we have to talk about these two terms individually, the strength and the matrix element. So I'm going to start with the matrix element as to why these transitions are so special. And I need to first introduce this concept of isospin, which was introduced a long time ago by Heisenberg. Basically, the observation was that in the absence of the electromagnetic component to the proton, which is charged, neutrons and protons are basically the same particle. So we can call that the nucleon. And then we can treat a proton and a neutron as simply an isospin projection or an isospin kind of particle where the proton is given a isospin down 1/2 state, and the neutron is an isospin up 1/2 state. And then we can talk about nucleons, and if we want to talk about neutrons, we're talking about spin up, or protons are spin down. And because we're now casting nucleons into a spin framework, we can then go to our quantum mechanics books and work out what's the total isospin then of an entire nucleus that has many of these spins in there. And you can then get a vector project or a vector sum then over all the different particles, depending on whether they are in their spin ups or spin down states. And remember, I told you beta decay, all that you're doing is changing a proton into a neutron or vice versa. And so the transition operator then in this simple framework of isospin would then just be a ladder operator. It changes an isospin down particle into an isospin up particle or vice versa. So you can go into your quantum mechanics books and look up what's the transition operator or transition probability for a ladder operator. And it'll look exactly like this, but you'll have S's in your quantum book for spins. We put T's for isospins, and that's the only difference. And for the very special case of T=1 type transitions, which is related to this projection here, the difference between neutrons and protons, you can just plug in the numbers and find that the matrix element is exactly 2 to the extent that isospin is a valid symmetry of the nucleus. So we don't even need a nuclear theoretical model to calculate for us the matrix element. We have it exactly in this isospin formalism for this very special case of super loud transitions. Okay, so back to our FT. So that's our definition. I've now replaced the matrix element by 2 if isospin is valid. The other thing is the strength that I mentioned. So is that a constant or not? And the answer is we think it is based on an analogy to electrodynamics. And this is something called the conserved vector current hypothesis that was postulated by Feynman and Gell-Mann in the late 50s. And basically in electrodynamics, you know that you have a universal coupling constant. You probably call it the elementary charge E. And so you know that if you take a proton of charge E by itself or you put it into a nucleus, it's the same elementary charge. The number never changes because it's a conserved or universal coupling constant. And by direct analogy with electrodynamics, it's believed that the weak interaction, which governs beta decay, also has a universal vector coupling constant, and we just call it GV. It's got a well-known or well-measured value, and that's this parameter up here. Okay, so if you put it all together, the FT value for these special transitions, it's a constant divided by 2, which is a constant, divided by G squared, which we also think is a constant according to the CDC hypothesis. And so everything should be constant, meaning the FT values for all these transitions are expected to be constant. Okay, so we can go measure that and check, are they all constant or are they not? And this has been work going on for 60 years by now. There's been a recent survey just last year on more than 220 independent measurements of half-lives, branching ratios, and Q values, everything you need for that FT calculation. And what you can see in the top plot is, yeah, they're pretty constant. But if you zoom by about 100, you'll see there are some small differences here based at the level of the precision. We've measured these things to extremely high precision, and we do see deviations on the order of about 2%, which indicates everything I just told you is approximately correct to within 2%, but there are some higher order effects that we have to put in there to understand these fluctuations. The most important one, at least in my view, is that this argument about isospin symmetry, that neutrons and protons are truly identical, we know that that's not 100% true. We see isospin symmetry breaking in all kinds of different nucleophysics measurements that we do. And so that breaking of symmetry between neutrons and protons leads to that matrix element to have a correction factor that goes in that we call delta C, which is a Coulomb dependent correction, which basically takes into account now the fact that protons are charged and neutrons are not. So there are some small differences in the transition matrix element. And so once you put in that delta C, you need a theory now to calculate all that. But once you do that, and it's a transition dependent correction, you can then correct each one of those individually and get to this plot here, which is a remarkably consistent plot showing that these corrected FT values are really truly constant at the level of 9 times 10 to the minus 5, which is a very strong validation of that CBC hypothesis I mentioned. But it also constrains the delta C theory itself, the other theoretical corrections that go in, and constrains any sort of new physics that might go above and beyond the standard model. So one of the ones that our group is kind of interested in is to look for deviations to this plot that could be created through the addition of a very small but non-zero scalar component. So in the standard model, beta decay is really a vector, an axial vector type transition. It's believed scalar is just 0, but we can look for if there were a very tiny amount of scalar present, then what would happen is it would cause a small deviation that would be proportional to the inverse decay energy W and actually cause this plot to look a little bit curved, depending on the value that you get for this constant that kind of determines the strength of that curvature. So this is a plot that shows now the dashed lines. If you had a scalar term on that order, then you would expect it to be bent up at these low mass nuclei. And you can see that the experimental data, even though it's perfectly consistent with a constant, it is kind of teasingly interesting to look here to see if these small deviations are the first hint of something new, or whether these are just statistical fluctuations about the constant. And so we can set limits on that quantity there by improving the precision in the measurements on the plot on the right. So that's what we've been looking at. We've been doing measurements lately on half-lives, branching ratios, on these lightest nuclei where this term is actually the largest, where you would expect the curvature to be the most. And we've been looking at carbon, oxygen, and neon through various measurements at TRIUMF, at ISOLDA, and even at GANIL. And the one that I wanted to talk about today was a recent measurement that we performed at TRIUMF to measure the half-life of carbon-10. What's interesting in that case is that we wanted to improve the precision, of course, but you can see here it's now a plot of the half-life versus previous measurements. So it's kind of flipped on its side. But you can see the most recent measurements in 2009 and 2008 actually are the most precise, but they also disagree with each other at the level of about 2.5 standard deviations. We wanted to figure out what's going on there and went ahead with a new measurement on the carbon half-life. So our experiment was performed at TRIUMF at the isotope separator and accelerator facility. That's the radioactive beam facility at TRIUMF. And we start with the TRIUMF main cyclotron, which is a 500 MeV proton accelerator that delivers up to 100 microamps of beam power onto a production target in the ISAC hall down in the target station. And that target is coupled to an ionization source. So from spallation reactions of the proton on the target, we can then extract out those ions and send them through a mass separator to choose the particular charge to mass of the isotopes that we want to study. So in this case, we'd set it for carbon-10, and then we can deliver that to our experimental area at really low energy. We just have enough voltage to get these particles transferred from one place to the other. There's no energy here for any kinds of reactions. So it's purely decay. We bring it to our detector and then it stops immediately and we can watch the radioactive decay. This is what the carbon-10 decay scheme looks like. The half-life is pretty long, 19 seconds. So we produce it at ISAC, we bring this to our decay station, and then it beta decays. And it's a simple decay scheme. You only have 2 excited states and 2 gamma rays that come out. This is the important 0+ transition. So this is the daughter 0+ and the parent 0+. So it's this super loud transition here that we're after. And when you have that radioactivity there, what's interesting is that in this particular case, the beta decay, of course, when it happens, you can just count the number of beta particles as a function of time to determine the half-life, which is what we're trying to do. It's a very powerful technique. You have very high efficiency for measuring beta particles, but you have no selectivity. So if you have contaminants that also emit beta particles, as you know, have a continuous distribution of energy. So you can't tell which beta particles are which, depending on or what parent they're coming from. So there's no selectivity, but you have extremely high efficiency. We did cycle measurements. So we bring the beam in this picture, we implant it on a tape, and we collect a sample, and then we turn the beam off, and then we bring that sample over to this little thing, which is a small proportional gas counter to measure the beta particles. And we collect for about 20 seconds, so that's 1 half-life of carbon. We stop and move the tape, and then we count for about 500 seconds, which is many, many half-lives, because we want to see the full decay curve all the way down to background. And in this particular case, you also see that almost all 98.5% decay to this state here, which emits a 718 keV photon, but even the beta decays above do also produce the same photon. So you don't have to use beta particles to measure the half-life. You could also just count the number of 718 keV photons with a gamma ray detector. And so we used this device here, which is called the API spectrometer, to detect the gamma rays and basically make another half-life measurement using the gamma ray activity. The beautiful part about it is you have very high selectivity because contaminants most likely don't have a 700 keV photon that they decay with. So you perfectly pull out the decay of interest, but the efficiency of the germaniums are pretty low. So the nice part about this experiment was we determined that if we're implanting for 20 seconds here, and then counting for 500. Well, for 500 seconds, we're not using the beam. So we decided, let's send it over to the other experiment and run the two simultaneously. And that's what we did. So we kind of ran two experiments for the price of one. This is what it looks like. So the top plot is the beta measurement. And you can see there is indeed a contaminant in there that we can tell differs based on the slope. So the other half-life is totally different from the one we're interested in. In the gamma counting measurement, you see there is no contaminants at all because we've gated on that transition. So the takeaway here is that the beta counting, you have more statistics because the efficiency is higher than you do in the gamma, but you have to potentially deal with contaminants. And in the gamma, you lose statistics, but you have purity. So they're really complementary approaches. In this particular case, in one cycle, so beam on and count, you can see the statistical precisions that we can obtain in both measurements. Again, gamma is higher because of the efficiency, decreased efficiency. That's a single cycle. And then we measured something like 550 of these cycles over the course of 4 days, determined the half-lives, and they agree beautifully between the two different detector setups. So that's a really strong test of the systematic uncertainties in our measurement as well. So overall, the final result was extremely high precision final result and 0.009%. And we determined it's actually the most precise half-life ever measured for carbon, but also the most precise half-life ever measured for any nucleus that we're aware of. And you can barely see the uncertainty on the beta measurement. You have to really squint. But you can see we're right in the middle of those two previous measurements with much, much higher precision. So with our new number then, we went back to this question of scalar occurrence in beta decay, and this new result actually sets an even stronger limit on the possible existence of scalars in nuclear beta decay. Okay, and I also just wanted to give a shout out to the person who kind of started this whole 20-year project to be able to get us to that point of measuring these phenomenally precise, ultra high precise measurements. And our kind of leader, Gordon Ball, was just awarded just last year the Vought Medal for contributions, kind of like a lifetime achievement award for these types of physics performed at TRIUMF. And this is an award given annually through the Canadian Association of Physicists. And our group did some nice work to make him a beautiful poster where we all e-signed it because we're not allowed to visit Gordon. Okay, so where are we now? Well, there's a new measurement to basically do what we did for carbon-10, but to do it for oxygen-14 as well. That article is drafted and it's actually on Gordon's desk. So that should be coming extremely soon. On the gamma ray side, I have two students working with me at the University of Regina who are going to look at the gamma measurement to then complement this particular brand new beta measurement for oxygen-14. The gamma measurement though, since that original spectrometer I showed you has been decommissioned and we've replaced it with a brand new gamma ray spectrometer called Griffin, which is a much more efficient spectrometer that's been in operation since about 2015 already. And our measurement is going to try to get the statistical precision on the O14 half-life down to about 0.03% from a gamma ray measurement. So we're working on that. Okay, so I want to move now as far away from stability as I possibly can and talk a little bit about silicon-22 decay. You can see silicon-28 is the last stable isotope. So this is six neutrons away, and it's the last stable or last bound silicon isotope. So it's on the proton drip line. It was first discovered in late 80s at GANIL. The first spectroscopy was in 96, where it was determined that it is indeed a beta delayed proton emitter. And you can see the proton spectra here measured in a gas detector. So these are actual proton peaks now. And they were able to do this spectroscopy with about 3 ions per minute at GANIL in the 90s. Today, the mass of this nucleus has never been measured. And actually, if you look at that separation energy for 2 protons, what's really interesting is in the atomic mass evaluation, even the present one, it still quotes a number that's strongly negative, which means that if true, that would mean that this nucleus, in addition to being a beta delayed proton emitter, could also decay by something called 2-proton radioactivity, which is super interesting. So what is it? It's an extremely rare decay mode. It was predicted in the 60s and discovered 40 years later or so in experiments at GANIL and GSI. There's only 4 cases confirmed. The most recent was in 2016, discovered at Weekend. Production rates are so low. It's such a challenging physics program to look at. But basically what happens is you have your parent nucleus, silicon-22 in this example, and due to pairing effects, you get that the daughter nucleus, actually the energy is higher than the parent, but then the 2-proton daughter actually drops back down again. So this is the odd-even staggering of pairing. And so it's actually energetically possible for silicon to emit 2 protons down to magnesium-20, but it is not allowed energetically to emit those protons sequentially. So you cannot have 1 proton followed by a proton, but you can have both emitted simultaneously. And the picture kind of looks like alpha decay. You've got this kind of cluster of 2 protons that are sitting in there, and they're bound by the nuclear potential, but they can, in principle, tunnel out, and then you get these 2 protons being emitted simultaneously. And there's a lot of interesting physics, like what's the nature of the decay? Is there any correlation in those protons as they're coming out, and so on. So it's kind of this extremely interesting and exotic decay experiment, or decay mode, I should say. So our experiment was performed at NSCL, looking at silicon-22, now with a production rate of 50 ions per second, as opposed to like 3 per minute at GANIL. You can see very clean particle ID. We've got some contaminants, but none of them emit protons. So all the protons that we see must come from the parent silicon-22. This is what our spectra looks like. They're the same spectra, but I zoomed the y-axis by 10 on the bottom, so you can see the structure. We see about 15 new protons. We've got a candidate for this beta delayed 2-proton event or channel here at 5.6 MeV, and that allows us to determine the energy of that analog state and as well its branching ratio. This is a plot of the exponential decay, so we can determine the half-life as well, only 31 milliseconds, in good agreement with the previous measurement from GANIL, but of course much more precise. And now, since we measured the branch, we measured the half-life, this particular decay is also a super loud decay. So even though we haven't measured the mass, we can deduce it from the fact that we expect the FT value to be constant. And if you do that, you determine a mass of that ground state, and then can calculate this 2-proton separation energy. And what we find is it's actually strongly positive, meaning that silicon-22 energetically cannot decay by a 2-proton radioactivity. So it's a pure beta delayed proton emitter, which is consistent with what we observed. The fact that we see all these beta delayed protons means that at least that channel is significant. Okay. And I also just wanted to highlight another experiment that I worked on while I was at NSCL from a group led by Zach. And I don't know if he's on the call, but I wanted to add these slides from an experiment that we performed a couple of years ago. And it was basically looking at, again, beta delayed proton decay, but to study a nuclear astrophysics topic, which was related to the waiting point in the ERP process of selenium-68. So you can see that here. And the proton drip line does this kind of interesting dance all around here. And so what happens is you can have selenium-68 gets populated here, but if you have a proton capture up to bromine, bromine's unbound, so it just drops the proton back. And then you kind of have to wait for this nucleus to beta decay, which can take a long time, 35 seconds. So that's the waiting point. The question was, could you bypass it through a double proton capture up to krypton 70? And at the time, if you want to determine whether that's possible or not, you need to know that separation energy and the uncertainty on it was pretty significant back then. So the experiment was to look at beta delayed proton decay using the same setup as the silicon experiment. It was actually run in campaign. And the nice part about the beta decay is you start from the parent, it beta decays to this unbound state and then emits that beta delayed proton back to selenium. So basically what you're doing in beta delayed proton decay is studying the inverse of the selenium-68 proton capture reaction, which is of course an indirect method to kind of get at some very interesting properties that you need for the astrophysics side. So the beta decay passes through those unbound states and then we see the protons come out. This is what the final spectrum looked like. You can see here we saw a really low energy proton at 640 keV. That tells us what the separation energy then is. And then from that, we can directly go back and calculate, for example, the luminosity on the X-ray burst light curve. And you can see these little red bands are the uncertainties on the experimental measurements compared to other kind of guesstimates as to what that value could be. So it's the beta delayed proton being the inverse of this sort of proton capture reaction, which is so important to the RP process, means that these types of studies are not just interesting from a nuclear structure point of view, but hugely interesting for nuclear astrophysics experiments where you are able to measure those very low energy protons. So the excitement that I have for silicon detectors and measuring protons has led me to start another project called the Regina Cube for multiple particles, which is a silicon detector cube that we will put inside the Griffin spectrometer at TRIUMF and basically perform these types of studies. There's some details here about the project itself. We got funding, and I've got a couple of postdocs working really hard during this crazy pandemic time to kind of get this all set up. And when we're ready, we're gonna test it all at the University of Regina and then ship it off to TRIUMF. It's just a photo, so the detectors have now arrived, the 6 detectors that make the cube, they're in the lab. For the structure itself, the frame, we've actually got it, been doing it on a 3D printer. So you can see here's the cube without the silicon. And there's one silicon detector installed on one of the sides of the cube, but the frame itself is 3D printed right here in our lab, which is kind of interesting. And also we do not just cubes, but we've been also involved in making headbands. This is our postdoc, Miran, who started this project to make headbands for face shields kind of at the beginning of the pandemic. This is a kind of CAD sketch of what the cube's going to look like. So the beam will come in along the beam line, and then we've got the cube sitting in there, and we're going to implant the activity on a catcher foil that I don't show here, and then the protons will come out and we'll detect them on the faces of the cube. So we're going to assemble starting basically now, and hopefully in 2022 can be running experiments at TRIUMF. And of course, it will then go inside of Griffin and sit inside this reaction chamber here. Okay, so silicon is super interesting, but you can't do everything with those detectors. And I'm also really interested in time projection chambers, using gas detectors to study the same physics. These are pictures here of an optical TPC you've probably seen before because a lot of these experiments were performed at NSCL, where you actually see the beam come in and then you see the 2 protons come out. So you basically take photographs of the decay process. And with one photograph, you can actually see the rarest decays because you only need one event. You just need a convincing photo to prove to the world that, that this decay has actually happened. So time projection chambers are something else I've kind of been working on for a number of years to be able to make beautiful images like this. How it works, I'm gonna kind of skip this a little bit because I've got some cool movies, but basically as the particles travel through the gas, it ionizes, and then in an electric field, you pull all those ionized electrons down to a pixelated pad plane, so it kind of acts like a digital camera. The more pixels you have, the kind of better resolution you get. And our project is extremely high density. We wanted 25 channels per square centimeter. So for our detector, 16,000 channels have to be read out. And we did a lot of work to develop the electronics, but also the mechanics of that. I'm going to skip over 5 years of work, basically going from prototype all the way to first experiment. So we built it. It's a project that was funded through the European Research Council at GANIL. We built it at GANIL. The project just ended in 2019. We ran a couple of experiments and have several more, but of course this year we will be participating remotely for those. This is a picture of it sitting on the GANIL beamline. So you can see all these electronics here to read out 16,000 channels down to our electronics. And these might look familiar to you because it's the same electronics in the ATTPC at NSCL. So we collaborated with them on the electronics part of this project through something called the GET, or General Electronics for TPC project. So you might have seen these sitting around NSCL. Okay, so we ran, one of our first experiments was actually to look at, again, radioactivity, but in this case was the proton decay from a highly excited isomeric state in nickel-54. So it's not ground state proton decay, but it's an excited isomeric state that emits protons. And at the beginning of this, it was only assumed to emit protons because there was a gamma ray intensity seemed to be missing. And so it was hypothesized that maybe it's because it doesn't decay by gamma, but by protons. And so the purpose of the experiment was simply to go and look for those to see if we can connect those to the proton daughter, cobalt-53. So does this isomer emit protons or not? It's super challenging, like the half-life of that isomer is only 155 nanoseconds. So from the production down to measuring everything, you have to be really quick or you're gonna miss it. The experiment was performed at the Lee's facility at GANIL and was our first ever decay experiment with the TPC. And I'm just gonna show you movies because that's the best way to explain how this works. So over here on the left is kind of a cartoon movie that I can't access right now. Okay, so what you're gonna see is the nickel beam comes in, this is in its isomeric state, and this cloud are the electrons produced. And so those are the ones we're gonna collect out. And then after that ion stops, we then wait for it to decay. So there's a time delay between the electrons that are produced from the proton to the electrons produced from the beam. And eventually those drift down in the electric field. We measure the charge on the pixels. And from that information, we can then extract both the lifetime from that time delay, but even the proton energy, which is related to the track length. So in the other movie here, it's the same thing. So you're gonna see the beam comes in, and for every event, we measure the lifetime, the delta T here, and the track length to give our energy. And so you're gonna see these accumulate. On the left are the track lengths for an event by event, and on the right are the lifetimes. And then we can just see for all the events what this actually looks like as it runs through the events of our experiment. This is real data, it's not a simulation. And we measured hundreds of these over the course of our experiment. And you can see we have extremely good resolution to separate out the two different protons that we expected to see in the isomer decay. And we can measure the lifetime quite precisely through this timing difference technique. So all these videos were produced by my colleague, Jerome Giovanezzo at Bordeaux. So thank him very much for these movies that are super instructive on how this all works. And Jerome has just submitted this article to Nature Communications earlier this year. So we're hoping to have this published really soon. Okay, we have an experiment actually coming up in May, where we're gonna look now at 2 proton radioactivity in a TPC. This just shows you, again, it's super rare. This is an older measurement here from 2011, where they measured only 7 total reconstructed events, but you clearly see the 2 proton nature in the TPC. In our experiment coming up, we hoped for like 8 per day and to run for 15 days. So to see about 120 events or so. So significant improvement with our new TPC compared to the older measurement. Okay, and the last thing I wanted to present was another measurement kind of idea. It's only a letter of intent at this point, but it's related to some interesting nuclear astrophysics. And that is to actually look at the 2 proton decay of an excited state. So kind of like the isomer decay that emits protons, there's actually a state that we think might emit sequential, in this case, 2 protons. And this particular nucleus is an excited state in neon 18. It's actually sitting right as one of the breakout points to the HCNO cycle, which is kind of drawn in this reaction network here. And it turns out that in neon 18, this one state that we think emits 2 protons is actually the most dominant resonance state in terms of the contribution to that breakout pathway. But there's this huge uncertainty on how that state actually decays. So if I show you the level scheme here, this is the state 6.15. And most of the time it just emits protons back to fluorine-17. But you can see here, there's this wide open space between 7 MeV and 4 MeV where you could actually just emit a 2-proton right through to reach the oxygen ground state. There's even a possible alpha branch, right? So like a p-alpha transition that could go from the 615 down to 014, which has never been measured. Our focus though is the 2p branch. There's huge amounts of uncertainty on what the branching ratio is, basically ranging from 0 up to like 30%. Of course, if the 2p branch is really strong, that's going to change a lot on, impact significantly on those rate calculations. So basically the experiment is, we want to populate that resonance with our inside of our TPC using the fluorine-17 plus proton reaction, and then using this beautiful technique of the TPC, measure those 2 protons directly and have this unambiguous proof that this resonance is actually decaying that way. And then its branching ratio will tell us about whether or not that impacts the reaction cross-section and kind of slows down the HCNO breakout process. Okay, so in addition to the experiments I talked about at GANIL and this LOI that we're developing, we want to bring our TPC to TRIUMF in Canada. We also have experiments approved at ISOLDA and at RECON. So there's really going to be lots of amazing physics to come using this really powerful TPC technique. Okay, so with that, I hope I gave you a kind of overview of all the different things we're working on. Many of the unobserved nuclei hold answers to big questions, and these decay experiments cover such a wide range of scientific topics. And a lot of the work that goes into it is not just studying the physics behind it, but developing the technology that we need to study it. And so we're doing experiments today that we never dreamed of. And decay experiments are really the frontier. There's enormous discovery potential, and it's such an exciting time to be working. And so with that, I just want to thank you so much for the invitation. And if you have questions about the other RCMP, then feel free to ask me, but you can see here, this probably looks familiar to you. So thank you very much. And this work was made possible by all kinds of different collaborators over the years.
So thank you, Gwen, for the wonderful talk and all those exciting results with your TPC detector. We are now open for questions, so you can unmute yourself and go ahead and ask the questions. Or if you want, you can write in the chat box and I can read them out. Okay, so I see we have, yeah. Please go ahead.
Yeah, can you hear me?
Yes.
I hear you.
So there was something unclear to me in the table that you showed that compared the half-lives of the different transitions, you know, the allowed, the forbidden, etc. So you said that the forbidden transitions, these nuclei that decay by forbidden transitions, have very long half-lives because there are other channels, more allowed, I guess, channels that allow them to decay more easily and I guess more quickly. However, these are the half-lives. I mean, if we look, for instance, at vanadium 50, it's not that there is another channel that allows it to decay faster. I mean, this is the half-life of vanadium 50. So, what is it that I'm missing?
I think it was just that what I had said was the only reason that we see these fourth forbidden transitions, the 6 to 2, and the reason why this half-life is so long is because there is no alternative for this particular nucleus to decay. So that's why we only see a very small fraction of them, because if chromium, instead of having a 2+ state, had a 5+ state somewhere, then of course this would switch to an allowed transition and you would never see the fourth forbidden branch anymore. The half-life would jump way up. So these rare ones we see are only because there are no other states for them to decay to. So they're just stuck in this really long loop waiting to decay by this much more difficult pathway.
Okay, thank you.
Yeah.
Okay, so there's one more question from Kathleen Trey. She is asking, what material did you use to 3D print the silicon frame, and how is the outgassing?
Yeah, those are great questions. So the first question in terms of the material used, so it isn't complicated. It's called PLA, polylactic acid. It's a standard plastics that you can buy for these 3D printers. You actually see it on the spool back here. It comes as like a small circular diameter rod, and it just spools into the printer. So it's the standard, one of the standard materials used in 3D printing. The second question was related to outgassing. That's definitely a concern. And we've done a few tests so far with the material in a vacuum chamber. It seemed like, at least in the small test environment, it was working okay, but it's something that we're going to explore in more detail in the coming months or so as we test it in more detail. Yeah.
Okay, I have a similar question just related to this. So you have like a cube there. And so I could see in your slide that you have like a slight projection there. That's for the beam to enter, or?
Yes,
like...
exactly. So
okay,
that's
cool.
this picture. We have
Yeah.
to open the doors a little bit to get that beam into the center of the cube.
Okay.
And that's, yeah, it's unavoidable. You can see it on the 3D print. That's this vertical slit here. So the beam is going to go right through that vertical slit. Yeah.
Okay, cool. Okay, so there's another question from Liji Sun. So on slide number 37, it says, I can see you observed a very nice 2-proton peak at 5.6 MeV. Is there any 2-proton correlation result?
In this experiment, we don't have access to the correlations here because we actually implanted our ions directly into a silicon detector, and then later in time looked for the particle decay. And so I say it's a candidate for beta 2P because we never actually observed the 2 protons at the same time. We observed their sum because they just sum up in the implantation detector. So there's a couple of arguments I could give you as to why I think it's a 2-proton peak, but I can't give you something as convincing as like what a TPC would be able to tell you. And we certainly don't have any measurements of anything individual with respect to those protons. So correlations are totally out of the question for this measurement.
Okay, good. If I may just ask, what kind of proton detection efficiencies did you have, like for these higher energies? Or?
Yeah, I'd have to think. I mean, well, even up to about 6 MeV, a proton will stop in a few hundred microns of silicon. So if I remember this experiment, the efficiency was almost 100% all the way up until 5 or 6 MeV, and then it kind of drops off. So, and that's again because we're implanting the isotopes directly in the silicon. So when they decay, like there's no solid angle or any losses to think of. We just record them immediately in the spot where we put the beam. So we only lose efficiency if there's such high energy that they actually go through the implantation detector and then escape off the surfaces, which can of course happen, and we need to correct for that for the high energy ones.
Okay, okay, good. Okay, any other questions?
I have a question.
Mm-hmm.
Hello, it's Gordon talking. I
Brilliant.
really enjoyed your talk very much. I had a couple of questions. Well, one is really related to the experiment using the TPC at TRIUMF. What is limiting it to being a letter of intent? What's required to make it actually a full proposal?
So yes, well, we submitted, maybe I can just throw this up, that will help. We submitted an LOI because it's not worth it to us to bring the detector from France to run a 5-day experiment. So we wanted to submit many experiments to run a campaign. So the LOI was to see whether or not the PAC or the EC thought that was a good idea to bring this thing from France and run many experiments. And then at the last pack, we submitted it, and a couple of experiments. One was approved. This one I just mentioned was deferred. So we now have to go back to the pack to answer a few more questions that they had about it. But we're hoping to kind of get a minimum number accepted before we put in the effort to bring this all the way over.
Yeah.
So there's no beam restriction at all. It's just we need to get a few more approved before it's interesting enough to do this.
Thanks.
Yeah.
Thanks for giving me recognition. You do all the work. You've done a lot in that program yourself. So thank you very much, Gwen.
Okay, so any other questions?
I have one more question about the silicon cube that you're building. So what kind of material, what kind of foil do you use for implanting the incoming beam at the center of the structure?
We haven't got that far yet. We have ideas, but we haven't actually tested anything. In the past, in other experiments like this, they've used really thin carbon foils, so a low-Z material to try to minimize the amount of energy loss as the protons come out. That's one of the things on our to-do list, is to order some of these and see how thin can we make it without it being so fragile that we break it every couple seconds. So another thing we're looking at is even like a plastic, like a mylar kind of catcher or something, but it just has to be low Z and it has to be thin, and it can't be very fragile. So we have to kind of figure that out.
I see. Do you expect any weird background from fusion evaporation reactions that could potentially?
No, because the beam energy is like 30 kilovolts. There's literally no energy to do anything except bring it to us. So.
Okay. Thanks.
Yeah.
Any other questions? Mr. can have maybe one more question if anyone has. Okay, all right. So I once again thanks Gwen for the wonderful presentation and accepting our invitation to present her work today. Thank you. And we shall meet again in 2 weeks' time for the next IRENA online seminar. I wish everyone a very nice weekend ahead. Take care. Bye-bye.
Thank you.